FEMAP with NX-Nastran has the ability to predict the performance of rotating systems with the NX-Nastran Rotor Dynamics Analysis module. In this video, the performance of a Laval rotor system is analyzed. To begin the analysis of the Laval rotor defined by shell and solid elements, open the FEMAP model, Rotor Solid Hub Start. Both the shaft and the hub are comprised of a 4330 alloy steel. This material's attributes were loaded from the FEMAP Metal Alloy Metric Materials Library. The shaft is meshed with 6 mm thick shell elements, and the hub is meshed with solid hex elements. Rotor Dynamics also requires that all rotating bodies have a coordinate system defined with their z-axis aligned with the axis of rotation. For the Laval rotor, coordinate system 101, rotating reference has been defined. This model will also use rigid elements to connect the start and end of the shaft to bushing mounts. After toggling off display of the shell property for the shaft, I'll toggle on display of nodes and curves. Next, a single node is created at both the centers of the start and end of the shaft. Using the nodes just created as the independent nodes for rigid elements, a rigid element is created at each end of the shaft. The dependent nodes are defined by selecting the curves at the start and end of the shaft. Both ends of the shaft are being supported with NX-Nastran spring damper elements. Before generating those, a nodal constraint is added to the beginning of the shaft. That node's Z translation and rotations are being constrained. In this step, a NX-Nastran C-bush property is created to mount the shaft at its ends. The translational stiffness is applied to the local X and Y directions along with translational damping. The two C-bush elements will be grounded and coincident to the start and ends of the beam. A FEMAP API script under the Custom Tools Meshing menu, Create Grounded C-bush Elements, is used to automate the creation of mounts by locating a node with permanent constraints at the location of each selected node and uses the selected C-bush property. Groups have been defined by properties in this model. Rotor Dynamics requires the definition of a rotor region for each rotating body in the model. A coordinate system with its z-axis aligned with the rotor's axis of revolution is selected, a damping frequency is assigned, and the nodes that define the rotor region are selected. The resulting rotor region is shown highlighted. Once the model has been defined for rotor dynamics, a new normal modes analysis set is created. Expanding the analysis set allows access to the NX-Nastran modal analysis options. For rotor dynamics, a complex solution is required, and in this case, the complex Lands code is chosen along with setting the solution type to modal. A frequency range of 1 to 500 Hz is specified along with the first 10 modes. Next, the Nastran rotor dynamics options are defined. A rotating reference system is selected. A step size of 100 and the number of steps is set to 250, making the range of analysis from 0 to 25,000 RPMs. Output units are set to Hz and the mode, whirl output is set to 17,000 RPMs. The analysis is launched from within FEMAP, and the analysis monitor is displayed. Once the analysis is completed, FEMAP automatically reads in the results of the analysis. After the messages pane is retracted, a deformed complex mode shape is displayed using the post-processing toolbox. FEMAP automatically generates curves for display of the Rotor Dynamics Campbell diagram as FEMAP functions. After expanding the functions object tree in the model info pane, the Rotor Dynamics 1P and 2P curves are displayed in the XY plot window. Frequency versus RPM curves for frequencies 1 through 5 are added to the XY plot showing the Campbell diagram. Crossings of curves or curve inflections indicate critical speeds in this design.